Hello and welcome to this didactic unit about training data and feature engineering. Once the data has been collected, our aim is to create training data to train a machine learning model. From the data science perspective, training data encompasses all the data used in the developing phase of machine learning models, including the different splits used for training, validation, and testing. Remember that, like other steps in building machine learning systems, creating training data is an iterative process. There are several techniques to obtain good training data. Let's see what they are. Sampling is a technique to select data. The sample subsets should represent the real-world data to reduce the selection biases. There are two families of sampling: non-probability sampling, when the selection of data is not based on any probability criteria, and probability sampling, which helps to reduce the selection biases. The simplest form of probability sampling is simple random sampling, which gives all samples in the population equal probabilities of being selected. Most machine learning models in production today are supervised, which means that they need labeled data to learn from. For example, a sample can be labeled as dog or cat, meaning that it belongs to the class dog or cat. The performance of a machine learning model still depends heavily on the quality and quantity of the labeled data it's trained on. There are two labeling methods: hand labeling, which requires human annotations, and natural labeling, where labels can be inferred from the system. Class imbalance typically refers to a problem classification task where there is a substantial difference in the number of samples in each class of the training data. This is expected in real-world applications. For example, in credit card fraud detection, most transactions are legitimate and only a small fraction are fraudulent. Class imbalance represents a challenge because the model cannot learn to detect the minority class. A usual approach for handling class imbalance is resampling, either adding more instances for the minority classes oversampling, or removing instances of the majority classes undersampling. On the other hand, data augmentation represents a family of techniques that are used to increase the amount of trained data. Traditionally, these techniques are used for tasks that have limited training data, such as in medical imaging. However, they have shown to be useful even when we have a lot of data, since can make our models more robust to noise. In this unit, we also cover feature engineering. Feature engineering is the process of choosing what information to use and how to extract this information into a format usable by your machine learning models. Features obtained following this process are what we call engineered features. On the contrary, features that can be automatically learned and extracted by algorithms are learned features. That is why the learning is sometimes called feature learning. However, we are still far from the point where all features can be automated. Also, the majority of machine learning applications in production are not deep learning. There are many operations developed to optimize the process of feature engineering. Some of them are handling missing values, scaling, and discretization. When handling missing values in data, you can either fill in the missing value with certain values, imputation, or remove the missing values, deletion. Feature scaling is used to scale features to have similar ranges, whereas discretization is the process of turning a continuous feature into a discrete one. Data leakage refers to the phenomenon when a form of the label leaks into the set of features used for making predictions, and this same information is not available during inference. For example, an AI tool to detect COVID-19 from medical scans can fail if the model learns the text form that certain hospitals use to label the scans. Finally, in general, we can say that adding more features leads to better model performance. However, having too many features can be bad for your model, since there are more opportunities for data leakage, can cause overfitting, and can increase memory required and inference latency when doing online predictions.